Okay, in this video, we're going to look at the particle in the box in one dimension and compare that with the particle in the box in 3 dimensions. Just to remind you, for the particle in the box in 1 dimension, we calculated the energy values as a function of n, given this using this equation. Where h is Planck's constant, n is the quantum number, 8 is the number 8, m is the mass of the wave particle, and a is the length of the box squared. So that's a. So that's in 1 dimension where all we're dealing with is x in the x dimension. When we have a particle in a 3-dimensional box, we have to consider both in the x, y, and z direction. So instead of a particle in the box, maybe you could think about this as a particle in a cube. So what we end up with is a potential well in x from 0 to a potential well in y from 0 to b, and I'm just changing the label of the box size so that we can separate x, y, and z. And then from 0 to c in the z direction. Each one of these dimensions, x, y, and z, has a corresponding size, a, b, or c, and has a corresponding quantum number, n. So to calculate the energy, again, just like this equation for 1 dimension, but the equation for the energy of the particle in the box in 3 dimensions is dependent on nx, ny, and z, and that's given by the formula h squared 8m, and then each dimension gets its own term here with the quantum number squared divided by the length of the box in that dimension. So now we can calculate the energy of a particle in a cube or a particle in a 3-dimensional box. So what are the possible energy levels for the particle in the cube? I've rewritten the expression from before for the total energy values if we have x, y, and z. I've rewritten the equation one more time. This is the case if it's a perfect cube where a is equal to b is equal to c. That would be the energy. Notice I've combined a, b, and c together as a squared in the denominator if it's a perfect cube. So we're going to use that for this kind of example calculation right now, where it's a perfect cube where a, b, and c are equal to each other. If a, b, and c are not equal to each other, you have to use the expression here that accounts for those different dimensions. Okay, let's go ahead and look at the possible energy values, and we'll look at the low energy values and the high energy values. So for the particle in a 1-dimensional box, our lowest energy level is just n1. For the particle in the 3-dimensional box, the lowest energy is nx1, ny1, and nz1, where everything is in the n equals 1 level. So we would write that this way. It's the E111 level, and that would be equal to, or its energy would be equal to h squared 8m a squared multiplied by 1 squared plus 1 squared plus 1 squared. That's how we calculate the energy of the lowest energy state. That gives us the value h squared 8m a squared times 3. So if we were to put that energy level, that E111 level, Over on our energy scale, it would look something like here. It would be about there. That's our E111 level. That's the lowest energy level. Let's calculate the next highest energy level. The next highest energy level is where the wave particle is excited in only one of the dimensions. That would be the E112 level. Now notice this is equivalent to the E121 or the E211 level. It doesn't really matter where the 2 is in this case because X, Y, and Z all have the same box length. So those are all degenerate or equal levels. To calculate that energy level, it would be 1 squared plus 1 squared plus 2 squared, which would give us an energy value of 6. So here is the E112 level. Notice that I'm simply putting the energy levels in terms of, or in units of h squared divided by 8ma. So I'm simply recording the kind of numerical value there of the energy I'm calculating. Okay, let's go to the next highest level. That would be the E122 level. To calculate that, it would be 1 squared plus 2 squared plus 2 squared. That would be the E equals 9. E122. The next highest level would be the E113. 1 squared plus 1 squared plus 3 squared to give us a total energy of 11. That's our E113 level. The next highest energy would be E222. That would be 2 squared plus 2 squared plus 2 squared to give us a total energy of 12 times h squared divided by 8ma. That's here. That's our E222 level. The next highest energy would be E123. 1 squared plus 2 squared plus 3 squared for 14 times h squared divided by 8ma. So that's here. And let's do one more. E of 223. 2 squared plus 2 squared plus 3 squared would give a total energy of 17 h squared divided by 8ma. So that's how we use the three-dimensional particle in the box model to calculate the allowed energy values for the wave particle transitioning between those eigenstates. We would calculate the wavelength of a photon required to do this transition just as we would any system. If we start, let's say, with the electron in the ground state, and we shine a photon that excites the electron, E equals h nu equals hc over lambda. If we shine a photon that excites the electron from that ground state to this excited state, we would simply calculate the energy of that photon by the delta E between those two states, just like we would for the one-dimensional particle in the box.